So we're getting going here. Think I made an announcement last night about the webcasting. See if anybody's there. So it's real easy. If you want to connect, if you can't make it to class someday and you want to just connect in real time, you can just go to this URL, which I think I have posted on the homepage. No, I'm just sort of trying it out, see if anybody, maybe nobody needs it in this class, but you click on this link, view live streaming lectures, and it will take you right there. And it's a real easy to use streaming program. It's the same one I use for my online office hours, so you can get used to that, and then you could tap in on Sunday night or Sunday nights, yeah, if you want. So I will leave that. All I have to do is share my screen, and then people tapping in will be able to see what we're doing in class. And you can also ask questions. So how'd it go with the stuff from last week? Everyone pretty much get that done? Any issues? Question? Yeah.
Can we go over the extra credit on the lab? It was like interlacing two bags.
Oh, the intersection of two bags? Yeah, the intersection problem involves, you know, you could, so inside that method, you got to create a new bag, right? And it's doing all kinds of interesting, maybe I should just not do this, but I think it's cool. Maybe I'll lower my volume a little bit. So you create a new bag, and there's a few ways you can actually do it. You can, this is a new bag to return, right? This is going to be the intersection bag. And you can also, you can make a loop, right? And, you know, while bag A is not empty, you can remove from bag A. You can sort of add to the result bag. Let's call this result. Is pseudocode okay? Does this sort of make sense? You can add to the result the remove from bag A. So what that actually means in code would be like, you know, that would be like result.add of bag A.remove. Well, actually, you don't want to do that unless that item is also in bag B, right? Because so maybe what you would do is you would say something like, okay, item test equals, you know, bag A.remove. You pull an item out of bag A, and then if bag B contains test, right, then you know it's in both bags. Does that make sense? Mm-hmm. So if that's true, then you add test. So you could say result.add of test, because it passed the test and it's in both bags, like that, right? The problem is after you do that, you're going to have eliminated all of the items from bag A. Bag A will be empty when you're done, and you were told not to actually, you know, mess with bag A. So you could make another bag like temp A, which is going to basically hold all the items you remove from bag A, so that when you're done, you can put all those items back in the bag A again, right?
Yeah, that's where I was confused. I was counting it.
Yeah, so it's kind of cumbersome to take everything out of a bag and then put it all back in again. And so there's another method that's really helpful for those kind of operations, which is called toArray. We didn't talk about it in class, but that's an easier way. You could say, you know, array, was it an array of string? I forget.
Yeah.
So you could say array of string data A would equal, you know, bag A dot to array. Actually, you can't do, it has to be an array of object. But if you say this, you will get all the items from bag A stuck into an array, and then you can check to see in a for loop. You can go through all those items in the array and check to see if they're also in bag B. And if that's the case, you add them to bag B. And in this case, you're not actually emptying out bag A. You're just getting a list of all the items that are in the bag.
Okay. And with the array, you can use regular indexing through.
Yeah.
Okay.
It would be data A square bracket I or whatever.
So
Yeah.
that's a much easier way.
Yes, that's how you would do it normally. But of course, whatever way makes sense initially is probably good. Yeah. Any other questions on the assignment? So is the schedule working okay? Everybody's getting everything done in time? And I think we have assignment 1, homework 1 is due like next Friday or Sunday or something? Next Sunday, I think. You check that out? February 19th. Yeah, a week from Friday, is that? Or a week from Sunday? Yeah, a week from Sunday. So, yeah, anybody there? Looks like we have a guest. Feel free to say hello. I wonder if I could disable those little droops it does all the time. It's kind of annoying. Well, I'm just gonna lower my volume so we don't hear that. As far as the assessment drills go, yeah, you have to realize that the assessment drills cover, you know, assessment drill 2 covers 2B, which we're talking about today. So you didn't have to finish the assessment drills by last night because we didn't cover stacks yet. Yeah, we're going to cover that today. Looks like we got a quiz coming up next week. We'll talk more about that maybe on Wednesday. Sorry, make what live? Oh, this is not live? Oh, thank you for telling me. I never get that. Let me see. I guess it's the module I have to make live. Thank you. You should be able to see it now. So you've already got the download, right, for this week, and you all also have the lab handout too, right? You can pull that lab handout out, that would be helpful. Oh, and on the subject of STEM tutoring, you got my announcement too, right? If you want to get help, we have these great STEM tutors. Riley, available on Monday, and looks like Friday. And we also have Amara, who can teach as she's learning. And we also have Chris, who took the class a long time ago and still is very hot and current on that stuff too. So you have 3 people that can help you. Right? Amara, do you mind helping people on this? Okay. Okay, focus on Chris and Riley. Yeah, they're old hands at this class. Okay. So a lot of ways you can get help. Back to the lecture at hand. So today we're going to talk about stacks. Another data type, and we're going to introduce another object-oriented term that we get in Java, which is something called the interface, which is a little strange until you actually kind of get used to it. You can use a stack. Stacks actually show up in a lot of situations in programming and coding. They're used to keep track of, like, whenever you do a method call, you have to place your current runtime environment, all the important features of what you're doing with the computation on a stack, so that when you finish the method, you can go back to where you started, where you came from. But stacks also are used in compilers to take your code and turn it into machine language. Stacks are implicit in human languages. They're also even show up in things like arithmetic. You can process arithmetic expressions using stacks as well. In fact, they're so awesome, there's a final project involving stacks you can do. So if you like stacks, you can make a really fancy stack, which is it's like a program interpreter. It's a command line interpreter. As you type in commands at the command line, it will actually process stuff for you. You can create variables, you can create functions, methods, and all that stuff is in the final project. It's really fun, hardcore kind of computer sciencey project. Today we're going to look at using stacks to process algebraic expressions, and that's sort of going to be the application of stacks that you'll get exposed to. But as we get there, we're going to kind of build up some basic understanding, basic capability of how to define and use stacks. You can also use stacks to check, how like when you compile your code and it says, well, reached end of file when parsing, it kind of ran out of like closed curly braces, and it still looking for a closed curly brace. It was parsing your curly braces. Well, you can use stacks to do that. You can use stacks to determine whether the delimiters in an expression are paired correctly or in your code. For evaluating arithmetic expressions, it's a runtime environment uses stacks. So the thing, it's a very simple structure. A stack is a collection of items where everything you add to the stack goes to the top. So you just keep adding stuff to the top of the stack, and it builds up higher and higher. The operation of adding to the top is called a push. And the only other thing you can do with stack is, well, you can check to see if it's empty or not, or full. And then you can check what the item is on the top. What does the top item actually have in it? And you can remove the top item, which is called a pop. Jacob?
For the final project, are we going to be able to choose like our own idea, or is it more structured, like 3 prompts or something?
For the final project, which we're not going to really get down to until like the last month or so of class, it's possible to do your own project, but most people will probably pick from a list of possible projects. The reason is you can do a lot more interesting stuff. There's some really cool projects you can do, and I can go over those sometime. Like there's like a genetic programming problem, there's a Huffman coding problem, there's a web crawler problem you can do. There's a bunch of them. There's like a dozen or more different projects you can actually tackle, which are pretty challenging, and they become a really good learning. You can kind of direct your learning to something that's appealing to you. There's even a really interesting project where you do image analysis of a physics experiment that are tracking like specks of dust in a cloud chamber or something, and watching how they move from molecular collisions, and from that determining what Avogadro's number is. If you're into like physics, computational physics, that's a pretty cool project. That came from Princeton. There's just a lot of good stuff on the final project list, and you can eventually you can kind of take a look and sort of see. I should probably post that somewhere you can see it too. But a lot of fun stuff on the final project. Back to stacks, though, you can see physically what a stack is: a stack of books, a stack of presents, a stack of bowls. Very common sort of thing, shows up in a lot of different situations. What we see here looks kind of like a Java doc for a class, but you'll notice something odd about this. It doesn't say class in the beginning, right? It says something new, which we haven't really looked at before. It says interface. And we're not going to do a lot of work with interfaces in this class, but I did want to just show you what they are and why you will run into them a lot more in the future. But for this class, they kind of get in the way, in my opinion. But we're going to show you a little bit about what that is. But anyway, you can see it. These methods are basically like the methods defined for a class. And they're defining what you do with a stack. You can clear a stack, you can check if it's empty, you can peek to see what the item is at the top of the stack. You can remove the item from the stack, or you can push an item on the stack. That's all. That's all you can do with a stack. It has less capability, I think, than a bag does. But this thing of an interface, this is the actual code for the interface file, and we're going to look at that in just a moment to get you experience with kind of what that is hands-on. Again, you can see these methods, but you'll notice there are no definition for the methods, right? It's just the prototype of the method in the interface. So what Java does, Java uses interfaces kind of the way C++ uses the .h files. If you took the 10C class, it's kind of similar to a .h file, a header file for a class. It just defines the class methods. And you use the keyword interface. And basically what an interface is, it's like a contract. It says if a class satisfies, if a class defines the methods that are with the signatures laid out in the stack interface file, then it can be used interchangeably with any other class that satisfies the method in the stack interface. This is, again, really high-level, object-oriented stuff. It's really conceptual, abstract. We're talking about multiple classes now that could satisfy, that could define the same methods in the stack interface. And the consequences of that means that object of the class can be stored in a stack interface reference variable. And that means you could have a stack interface reference variable can refer to objects of different kinds of stacks. And this is all very quite abstract. But in a moment, we're going to play around in the Lab 2B code, and you can see how BlueJ indicates what a stack interface is. It shows you this box here, and then this is the interface defining the methods, and then these are two separate classes that both define all the methods for a stack. Both of these classes have a push, a pop, a peek, a clear, and an isEmpty method. And because that, you can essentially store them in a variable that's defined as a stack interface variable. You can store them interchangeably in one of a stack interface variable can hold a reference to either objects of those. Hard to articulate. So, as an example, and we're going to explore this more once we start building our own classes. You can make an array stack. This is a stack that's based on an array. So inside the stack object, there's an array that keeps track of all the items in the stack. And it kind of internally, it looks something like this. You have an array with references to all the items in a stack. It's just a collection of items, just like the collection of items in a bag. Alternatively, you could make a linked stack. This would be a stack that uses a collection of linked chains, which we're going to explore next Monday, how that actually works, instead of an array that has some advantages and disadvantages, and sometimes one is better than the other. Both approaches have pros and cons. The point is, if both of these classes, array stack and linked stack, implement the stack interface, then you can pass them to like a method that's asking for a stack interface variable, and it will actually work properly with either one being passed to it. And so when you define a stack object, you can store it in a variable of type stack interface instead of a particular stack. So our stack would be one particular stack class that implements the stack interface, and you can create a string stack based on that and stick it in that variable. So I think that's abstract enough for us to kind of take a pause a bit and play around with the beginning of the lab, so you can kind of see what exactly I'm talking about with these interfaces. It's really important to So if you open up your Lab 2 folder and open up Lab 2B and open up the package file, and just so I have my prompt here, I'm going to open up the lab activity. So we'll create a stack interface variable and assign it one of those. So let's hear. So we're going to open up. Let's just compile this thing. And that's interesting. Do you see any? Did any of you have like the array stack or the link stack showing in BlueJ?
No.
Hopefully they're there. Let's just see. Hopefully they didn't disappear all of a sudden. Well, you can see it here, and sometimes BlueJ will pick that up and show that. But you can see there's an array stack class here in this folder, and there is a linked stack class in the folder. So I guess at one time they did show up, and that's why I was able to take a screen capture of it. The problem is I'm only providing the precompiled code for these classes, so that you don't get to see the answers. We're going to be writing those ourselves, so I wanted you to see how that would work without having them at your disposal, without being able to see the source code inside, because we're going to learn how that all works later. So what we can do, though, is we can open up the lab2b file. And here is some code. And we're defining a stack interface of string, st, which is a new linked stack of string. And we can print it out, and we can add some items to it and print it out again, see if it looks like it should. And when we run the code, we'll see, although initially the stack was empty, it just had null in it, eventually it has these 4 items. And you should notice that the first item is, the first item added is on the left, and the last item added is all on the right. Is anyone having problems accessing this code in any way, or having some issues?
Yeah, I can't.
Did you unzip it? Yeah, you have to unzip it. Yeah, you can't really work in the folder until you unzip it. Anyone else having problems? You probably still have it in the last slide. Okay, well, what's so great about interfaces? The thing is, instead of using the linked stack, because we have another stack object in there, we can, in fact, we can stick a linked stack in there, or we can assign st a new, if we want to, a new array stack of string. Why? Well, because if the array stack was defined according to the contract spelled out in the interface, if the array stack has defined all these methods that are written in here, if we have a push method, a pop method, a peek method, an isEmpty method, a clear, and a toString method, defined with those exact parameters and everything, then we have a class that implements this interface. And if it implements that interface, then we can make a variable of stack interface and assign an object of that particular class to it. This might not impress you too much, but it's interesting that the code compiles with a completely different class in here, a linked stack or an array stack. It compiles exactly the same. The reason is, of course, because however you define the stack, logically, both classes are behaving like a stack is supposed to behave. They're just representing things differently inside. Their internal bookkeeping is different. But logically, they're obeying and they're following the rules of how a stack should actually work. And one of the outcomes of this class is trying to get people to separate. This is the notion of this data abstraction. We're sort of trying to separate the logical description of what a class is supposed to be doing and the inner workings of how it actually is doing that behind the scenes. That separation is the basics of the abstraction that we're doing when we create these abstract data types. We start with a sort of a logical idea. What is the stack supposed to do? And then later we say, well, how are we going to make the code to implement the stack if we're, say, using an array or if we're using a linked list? Or maybe another way you might think of later. Those are some of the fundamental key outcomes of this class. It's hard to impress people because it doesn't really impress you when you see that, like, oh, big deal. But like, for instance, actually a good example was the Lab 2A, that intersection. And it might be worth just jumping over there real fast so I could show you what that would sort of look like. Just kind of taking one last look at Lab 2A. This would actually be a better example. I should add this to the slides. See this this intersection method? What if you have two different bag classes? One's doing a bag based on linked nodes, like I explained, and another's doing a bag based on arrays. If you define this method so that you accept a bag array or an array bag or whatever, right? Bag array A and bag array B. Sorry. Bag A and bag array of T, bag B, right? Then you can only find the intersection of two bag arrays or array bags. Well, it doesn't make sense. If you have another class that acts like a bag, you can't find the intersection of a bag based on some linked thing or a bag based on some arrays. Well, you should be able to do that, right? And the answer is, well, if you want to do that, you got to actually use a bag interface. You can define a bag interface. We didn't do that for the bag class, and define both bag A and both bag B as bag interfaces. Now, if we try to find the intersection of a bag array versus a bag linked or whatever, you could pass either one to either parameters. The interface variable can refer to either a bag array or a bag link, and then do the intersection operation interchangeably on those. Still not impressed? Let's just close that. Yeah, well, that's sort of the justification for interfaces. Now, I know it's not that exciting, and one of the headaches of interfaces is when you're developing code for later on when you're defining these things, if you decide you want to add a method, you have to remember to go add it to the interface as well as to the class that you're writing. Those have to be consistent, and quite often people will forget, and then you're just like, I got to make this thing over there. You spend a lot of time kind of keeping those things up to date, and it becomes an impediment to actually doing the problem solving of writing those methods. So we're just going to be kind of looking at interfaces at this level today of users, and then probably not really coming across them too much more. You'll see them again when you need to, when you're doing more advanced object-oriented stuff. So the next step, of course, is what happens when you use a stack. And logically, what a stack does, of course, is it actually lets you add stuff to the stack, and it builds up these guys. So when you add Jim to the stack, you have Jim at the base. If you add Jess to the stack, Jess appears on top. We're just stacking all these items up on top. And then you can remove them, but then when you remove items from a stack, they're always coming off the top of the stack. So this code is adding a bunch of items, showing you what's on the top. It's removing an item. This is what is removing an item. This is looking at what is the top item, and this is actually removing the top item. So, now you're supposed to do problems 1 and 2. So have you all done those already? So you can do problem 2 now. And problem 1, we've already done problem 1. Oh, we did? Let's see, did we do that? Let's see, make a few stacks using interface, array, and linked. And push and pop and print them. Make a few stacks. Well, we could, we could make another stack if you want to. So we could, for instance, we could do all this stuff with the linked stack and then add this thing down below, and now make an array stack, and we can push some items on it. You can print out, okay, well my new ST equals like that, because we've made a new array stack. You can pop an item, and you can just look at what the current top item is. I think it's called peak. In some definitions of stack, it might be called top, depending on what people have defined it as. There's a few different standards. Pop is the, push and pop are sort of the universal for adding and removing from the stack. And you can run this and just sort of see if it's working properly. So my new stack is lemon and apple, and we can pop the apple from the stack ST and then show the current top like so. This logical thing that allows you to add something at the top and remove it from the top. So here you can write a couple lines of code. Print the top item on the stack, but don't remove it. Actually, now maybe we want to keep the original stack here. So let's just put a /* here. We can save this for examination later, because you want to have a few items in the stack. So this will actually put have 4 items in it. So now you can write some code here that prints out the top item, kind of like we just did, And then another code that as long as the stack isn't empty, you can print and pop the next item off the stack. It's kind of like bag.remove. In fact, it's exactly the same as bag.remove. If you actually noticed the way the bag class worked, it always gave you the last thing you added. When you removed an item from the bag, it was always the last thing that was added. Questions? Anybody online have any questions? You know, if your video's off, there's a thing there you can put your name on, and then I can see who you are. Probably not even there. If a ghost audience. Or activity. Okay, questions on that? Y'all got that?
You probably just do. You need the parentheses. No, I can't. Hey, do you guys understand what a lot of this declaration is about? Like, you know how you call the ST a new bit stack? And then can you just say ST is equal to 0 Thank you.
Yep.
Yeah. Because there's two different things. There's a linked stack and then there's a array stack. They're not the same thing. Yeah, but like, aren't these using this variable in order to say here?
No, this is later.
So my question is like, what happens to like the elements?
We just demonstrated some of these, so
Yeah, I don't see what
yeah.
So like, you know how you declare ST here as a length stack? Yeah. And then you use ST
This is good, but I think we probably just.
Yeah. So like, what happens to like what is it? Like,
Does it just override it?
Like, does it just like
You're redeclaring it,
does it
right?
just like remove everything that was already in like the loop?
Like in the link set?
I think it does.
Here.
Oh no, because we usually can't do this like with other classes. So
That's what I was thinking. Like,
this is the first time we're able to like declare two different
That's definitely an ask removal.
Yeah, I put a slash there to add.
because like I was just thinking about it. And I
Top
was like,
item with a P.
because you usually can't do this. You guys can do it with this.
Oh my god.
We're at the hard things.
Oh yeah, because there's nothing to use that. Oh, it's just about outbound friend. It's just
You can delete how much
see, first it's checking if it's empty. Is staff, yes, empty. And then one stack ST equals and then it prints the stack. But there's nothing in the
What happened when you ran?
I got null because I commented out null.
I ran it.
Oh yeah, it just says tweets.
There should be what?
Yeah, isn't that what it just says cleats and then cap in the ball.
I just put mine back. Say it was like what you did earlier, but we counted out.
So try to do both of those. Print out the top item, and then as long as the stack is not empty, print out and top an item from the stack.
So this is supposed to be.
Yep.
This came up all weird. This is all weird. Well, mine's good.
Because you only have one left.
Mine's not right.
Oh, that's why.
Then you're going to have a stack that has these 4 items on it still. When we made SP a new array stack, we wiped out the old stack. We only have 2 items on it.
Oh, you're just gonna print out the stack every time it goes to the link.
So now it should work.
Yes, now you'll see we can do it.
I just thought it was our calculator.
Just do it. Oh yeah, we're gonna do the system that's on mine.
I'll go over that later.
Okay. Yeah. You just put that in the line.
Yeah, I had a question about so here you declare SC as a
Yep.
and then like you use the same variable like in the array stack.
Yes.
Like, how does that work?
I'm glad you asked.
Was he not intentionally
Why does mine go to?
Yeah, I'm kind of a spaz, so if people don't like it, what is that? Then I just keep on going. So,
Yeah, it's fine.
so thank you for asking. There was a couple people that asked this question. They were a little confused about this. How come? And let me activate this again. So what happened when I did this, and how come I'm able to do that? Is that your question?
Yes.
So let me sketch a picture of what's going on here. So what's happening is initially is we're creating a variable st, which can hold a reference to a stack, right? And we're assigning it a, oops, let me do that up here, right there. And the weird thing is, though, st is not a variable of a linked stack. It's a variable of type stack interface. Okay, and that's a different thing than what we've used before. The stack interface thing makes a variable, but this variable can refer to an object of any other class that fulfills the definition of the methods in the stack interface. The stack interface is not a class. It's actually a pattern for a class. So this is even how we go higher levels of abstraction. Right? What's a class? Well, a class is sort of like a blueprint for an object, right? Well, what's an interface? Well, an interface is kind of like a pattern for how you would have to organize a class to make an object. You know what I'm saying? So now we're like 2 levels up, right? And that's what happens in coding all the time. But this gives you the flexibility. That's right, because if you just made this a linked stack, and for instance, let's try this. I should have thought this through better. Let's just put a comment here, and hit enter here, and say linked stack of string st. This is how you're normally used to creating these things, right? You're making a linked stack object here. You should assign it to a linked stack variable, right? And that's all well and good, and that would work just fine, except when you come here, if st is defined as a linked stack variable, you can't store an array stack object in it, right? There are 2 different classes. So you'll get a compiler error. You have an incompatible type. An array stack cannot be converted to a linked stack. Okay. And yet, there's good reasons why you would want to do that. Like, for instance, if you're trying to pass to a method that's going to process a bag, and you don't care what the implementation is, you just have to be able to, or I'm sorry, pass to a method that wants to process a stack. You don't care what the implementation is, you just need to like push and pop stuff on and off the stack. So that gives you the flexibility to do those kind of things.
So is the data lost?
So going back to when this was actually working, right? And let's continue with the, let's go back to how that was and turn this back into a stack interface ST. And now that it's a stack interface, you can assign an array stack to it, no problem. But what happens when you do that, right? So let's continue this drawing. So we created ST, and we check to see if it's empty, and then we push these items on it, right? Well, ST is actually, this is actually a linked stack, although it really doesn't matter to us how it's doing it, and we'll kind of need to talk more about that later. But when we are adding stuff, let's just say we're adding stuff and it gets pushed over to the, let's just say, okay, we've got a ball here on our stack, and the next thing we're adding is a cap, and then we're going to add a mitt and cleats. This is a kind of a conceptual view of what this stack object is sort of looking like right now, right? You got these 4 items in it. So what happens when we say ST equals a new array stack of string here? What happens to the old stack?
Destroyed.
It's destroyed. What happens is ST gets routed to a new stack object, and this thing becomes orphaned. The link is lost, and the Grim Reaper, called the garbage collector in Java, comes around and looks for memory blocks that don't have anybody. It looks for variables, objects that don't have anybody referring to it, and when it finds them, it gobbles them up so it can reuse the memory again. So this thing gets wiped out, and we now have a new stack, and this happens to be an array stack on which we can then push lemon and apple. Does that answer your question?
Yes.
Something more important came up, I think. Any other questions on that? That's kind of an important thing of understanding what's happening there. Yep.
So when you're creating ST first, when it says like stack interface,
yep.
That whole thing, so does it mean like ST is a linked stack of pattern stack interface? Like is that kind of like the transition?
Your question is, when you say stack interface ST equals a new linked stack, are we saying here that ST is actually a reference to a pattern of stacks?
No, it's like ST like a linked stack of pattern stack.
Is ST a linked stack of pattern stack interface? No, it's a linked stack of string, right? And that's how you can tell. You look inside these brackets, and you see the word string.
Okay.
It's a.
What's the stack interface? What does it like refer to?
What the stack interface refers to is this code right there. And we're going to see more interfaces for certain situations. They'll come back again. So this is kind of a little weird thing to kind of throw at you. You can read about it in one of the appendices too. I think it's Appendix C. Yep.
I used an interface, so like different objects like a rectangle and a circle, and they all implemented the draw interface.
Yes.
So that way, when you're just calling the draw method, it doesn't matter if it's a circle or a rectangle.
Right. You can pass either one to it.
Pass a draw to this like one method.
So Jacob made a circle class and a square class or something, and they both had a draw method. And by defining that draw method, you could make an interface saying like drawable, and an object is drawable if it has defined a draw method.
Right.
That means you can pass, you can make a parameter for a method of type drawable, and you can pass any object that you've created for any class that has this, that satisfies this drawable interface.
So you don't need like 3 different lists, one for circles, one
Yeah.
for
Yes. Exactly. And none of these are great. That'd be a much better example. I'll have to do that next time.
Okay. No,
But
I like that. That's why I wanted
yeah,
to-
it's a really good thing, and we're kind of on this trail of tracking down these collection classes, which are more high level things. We're sort of working with these sort of high level stuff right off the bat. But a lot of what we're talking about here, it shows up in a lot of different situations. Another thing it shows up in is comparable. If you define a compare to method, then you have a comparable class, and you can pass it to anything that needs to compare stuff. But that will come back again when we do sorting. I don't expect you to have too much of an appreciation for it just yet, but it is sort of a preview, and the more you see it, the more comfortable you'll get with it. So again, how do we print the top item of the stack but don't remove it? We can say, system out print line and st.p, right? We just did it up above. And I'm going to comment out, I recommend because this line here erased the previous stack, which had 4 items on it, I'm going to comment that out. So that what we'll have is this original stack of 4 items, so that when we solve part B here, 2B, as long as the stack is not empty, print and pop the next item off the stack. As long as the stack is not empty means what? While not st.empty, right? That is empty. Well, that's true. Then you can system out print line and you want to print and pop. So the pop command is going to remove that object, remove an item from the stack and return it so that you can actually send it to the print line command and print it out. Okay, and when you run it, you should see something like this, right? Now we're popping, the top is cleats, now we're popping cleats, mitt, cap, and ball, and when we're finished, we won't have anything else to show. It's a null, it's an empty stack. Okay, so we're finished with problem 2. And now I'm going to need, so there's a few weird things we have to cover today, and I'm not sure this is the best way to do it. But some of the stuff that comes up in working with these collection classes that we're going to be doing, these stacks and bags and lists and queues, all these things, they may use an internal array or a linked structure, but these are arrays of objects that they're creating internal to it. What do we know about the object class? Remember, we explored that a little bit last time. If you make a variable of type object, what kind of object can you stick in it? Anything you want. That's like the universal variable. You can store any object of any class that you want in a variable of type capital O object. Okay? You can hold a reference to any object of any class. Okay. So because we're using this generic thing, we want to be able to make a bag of string and so on. But what Java does, internal to these things, it's making an array of objects, because an array of objects can store a reference to anything you want to stick in the bag. Unfortunately, you can't make a bag of primitive items. This is the weirdness of languages, right? It seems like a good idea. Let's make everything an object in Java. That was the intention of Java, but they still needed these primitive variables to store just basic tidbits of information like doubles and chars store. But since we're defining our classes so that they have an array of objects inside them, you can't stick a primitive inside an object variable, right? So you can store anything, but if you try to store a primitive into an object variable, it converts it into an object of a particular class. So Java actually came up with a solution which says, we're going to need to make these wrapper classes. So these are classes that have like capital D double, capital I integer, capital B boolean, capital C character. And basically, the name of these classes is the same as these primitive types. And all they do is they wrap these primitive values in an object. So it's like you have this complicated machinery inside of which is just this dumb little variable, right? And that's what these wrapper classes are. And Java did some extra work. These classes wrap these primitive values in an object. It provides, but the language provides this thing called auto-boxing and auto-unboxing so that working with these wrapper classes is almost transparent. Like you don't have to worry about casting from a primitive double to a class double. You don't have to worry about that. It happens automatically. So here's an example of auto-boxing. When we declare double number, a reference to a new double object with 2.34 in it, right? That's converting this double into a double class. And you're familiar with the idea of a primitive variable value, which we can assign a value to it. These are both initialized with the same value, but one's an object and one's a primitive. And this auto-boxing thing allows you to set value equal to number. Okay, because that means you've got the object here with the value inside it, and auto-unboxing says pull out, the inside of that thing and stick it in this primitive value. And auto-boxing says, take this primitive value and stick it inside an object, wrapped around it, right? That's what auto-boxing and auto-unboxing do for you. Question?
This might be on the scope of the class, but why not just define primitive values as objects from the get-go?
So we had a question that, thinking about how the language was defined, could they have defined the language to eliminate all primitives and just have objects? And
Why not?
I think your answer was correct. Would it be slower? It might not be that much slower, but I think it would take less room for one thing. One thing that's interesting is when we in my 10C class, which is a C++ class, we actually work with an Arduino, and the Arduino is a little microcontroller. It doesn't have a lot of memory in it, but it has a C++ compiler for it. And you can use these fancy classes like a string class to represent strings in the Arduino, but it takes up more memory.
Yeah.
And in the Arduino environment, memory is kind of limited. So you want to use things that take the least amount of memory. And that's one reason why you would still want to have primitives.
Yeah. When you make like huge programs, even though like one thing isn't that much, when you have like gigabyte programs, like,
Yes.
It starts to add up.
Yeah, yeah. And it's a very good question, and it would be an interesting experiment to write your own. And maybe someone already has a language out there that is only, Java without primitives. You could probably Google it. Someone's already done it, and they could tell you how it went. Now, these wrapper classes also have some, and I'm showing you this because we need to learn these things to do the actual lab today to make sense of it. So it's a little bit weird. I'm kind of going off. It looks like I'm going off on a number of different tangents, but this is all pretty important. You're going to see there's actually a reason why we're doing all these things. These wrapper classes also provide a number of utility methods for actually working with their primitive data. So it's a convenient place to stick a bunch of utilities for working with characters or doubles. So if you have a char symbol like X, the character class has a whole bunch of these static methods to tell if that character happens to be maybe an alphabetical letter as opposed to a number, or a digit as opposed to something else, 0 through 9. A digit is 0 through 9. An alphabetical letter is A through Z, or capital A through capital Z. So these methods will actually return true or false if the symbol is one of those things that we're checking. So in the integer class, you often have to take something that's read in as a string and convert that into a number. And that's what the parse int method does. If you try to parse int an actual string with no numbers, I think you get an error message or a null or something, but it handles those things. Okay, so we're going to try that out in problems 3 and 4 now. So activating the code here is showing us how we can create a stack interface of double. I guess I already did. But if you change this to lowercase double, if you don't trust me, you can see that it won't work. You don't have to do this. You can just watch. But if I do that, see, it doesn't work. You can't do a primitive there. But you can do this wrapper class. And essentially, you end up with the same thing. You now have a stack of double, capital D double. And it says, it suggests using the debugger to see the difference between number and value. This is actually kind of an interesting thing there. I think I can put a breakpoint here, and the class is compiled. And if you put a breakpoint, you can click in this column all the way to the left, and you get a little stop sign there. And what happens is when you run your program, it's going to automatically stop at that breakpoint. And you get the debugger interface. Now we've just declared these values, these variables number and value. And you can see on the debugger, can you see this? It's actually really small. I don't know how to make this larger, unfortunately. But if you squint, right, you can see that there's this double number and it says object reference there, right? It doesn't show you any value. And then it says double value, and you see the value right there, 2.34. You see that? That's the primitive value. And you can look at the contents of this value number. If you double click on this thing, it'll show you the object, right? This is the object. It's showing you all the junk around the object, right? This is sort of the encapsulation. It says it's a double class, and then here is the internal guts of that thing. This is the primitive inside the object, 2.34. If you click on the step button, you will advance to the next line in your program, supposedly. There we go. And now number should have been changed to 3.14. If you open this again, it now says 3.14. If you say value equals 3.1, if you do that line, you can execute that statement. But see, this is where auto boxing takes place. It's just passing into and out of an object this primitive value. And you can even multiply, a lowercase double times a capital double. A double primitive times a double object. That works as well, all through this power of auto boxing and auto unboxing. So you can then push these values onto a stack. You can push the sum of two values onto a stack. All these things are possible. And then when you look at value stack, you can see in your console, I think, are we done? Let me just continue, wrap that up. And this is the result. See, we can multiply, we can add stuff together, and that's our value stack. Okay, and that's the debugger. Very handy. You can try using that if you run into problems. Anything, everybody okay with that? Kind of converting back and forth with these wrapper classes. Okay, let's go ahead and comment that back out. We don't need to do this again. So you can go back up here and remove that slash. Now we're going to play around with these static methods, and in particular, the ones for the character class are kind of useful. Because they're static methods, you have to invoke them using the name of the class, though. So you have to say character.method name. You don't create an object of a character class to do this. And there is a character value. Now, you might not have realized, there's no, oddly enough, the scanner class, it doesn't have a next char method. It has a next int, next double. There's no next char method. If you want to read a char, one symbol, you have to read a string using like the next line method. And then from there, you can access the first character in that string. That's how you read a character from the keyboard. I don't know why, it's kind of stupid, right? But that's all you get. I don't think the scanner class is used a lot, by professional Java coders, right? It's kind of for us in education to try to, figure out how this stuff works. The professionals are all doing stuff with GUIs and all that stuff, crazy stuff, which we don't really want to get confused with right now. But we can check to see if a symbol that we enter is a digit, and by using the character.isDigit method and passing that value as an argument, we can check to see, we'll find out true or false whether it's a digit. If it's true, we'll print out that it is a digit, and we can convert that to a double using the getNumericValue method, right? You say get numeric value of this thing we just entered, and now you can store it in a double value. So that's pulling the double out of the char. Okay, so we can run this and try it and see. So type a letter, and it'll tell you if it's a digit. If we type, like, say, 3, it'll say it is a digit between 0 and 9, and the numerical equivalent is 3.0. You can try also typing a letter X, and it says it's not a digit. You could try another thing. Let's make a string word. Enter but we're going to have them enter a 4-digit number. And we're going to read it as a string. So we're going to set word equals keyboard dot next. Okay, well, how do we? So we can say, you entered. But how do we turn that? Supposedly, if we did enter a number, how do we turn that into an actual integer? Yeah, the parse int method, right, in the integer class. So you can say int, what are we going to call this thing? Call it I value. And we can say, you bring up the integer class, and you invoke the parse int method, on the word. And converted to an int okay, again, the value of these wrapper classes, all these utility methods they provide, is really handy. So we can see if a letter's a digit. We can also enter a 4-digit number like, 5, 6, 7, 8. And it has converted into an integer successfully there. Is good. The question is, what would happen if we had some things that weren't like an integer? What if we entered like, let's type A here. What if we entered 45.67? Oh, well, we get an exception, which says it's a number format exception, and that allows us, that's an exception, we can handle that. We're going to learn a little bit more on exceptions, I think, maybe next week, pretty soon. Anyway, so it flags that there was no success there. There was something in there that wasn't an integer, and it couldn't actually do the conversion. Okay, you with me? So those are the basics of things that we need to learn to be able to solve this RPN application, which is a very easy problem, but it's so weird because you haven't seen anything like this before. So I'm going to explain in the lecture now what this is actually all about. It's pretty cool. This is an example application of a stack that's quite functional, quite useful. This actually kind of happens a lot in our computer behind the scenes. You might not know this, but if you're taking the computer architectures class, you're going to see this as well. Stacks are a fundamental part of computer architectures. But when a computer has to process an arithmetic statement, something like this, this is a high-level language. This is something like Java or C++. What the machine actually processes are things called assembly language or microcode, machine language instructions, which might be something like this. We have to load in a value and store it in this register A, and then we have to multiply whatever was in A by whatever's in B, and then add whatever's in this register C, and then take the result and store it in this register called X. The computer can only do one thing at a time, so all these statements, have to be broken up into these, really minute steps so the computer can do it reliably and accurately every time. We call this notation infix, which means that the operators are in between what's called the operands, which are the values that we're processing. There's another type of notation called reverse Polish notation, otherwise known as postfix notation. And if you have like an HP calculator, you might be familiar with that. It's kind of a funny name. I don't know. Is there a forward Polish notation? I've never actually researched it, but most compilers actually have to convert the expression from the infix that we're used to typing it into postfix because that's how the hardware actually wants it. And that means we got to put the operators after the operands. So instead of saying A times B plus C, you write A, B star, C plus. Jacob?
How is that not having parentheses? How is that going to be different?
And yeah, the advantage is you don't have to write parentheses.
You still get order of operation there.
So why is it good not to have parentheses?
Or like why? How is it